So Mia is one of our first class of robotics PhD students here at the University of Michigan. And she also was one of the students who just immediately found a job, right? And so the job search is very short. So
yes.
I don't want to get into your research because you're going to tell us all about that.
Yes, I think that's the plan. All right, well, thank you very much, and thank you everybody for being here. And I guess we can just get started. So as you can read, this is geofencing for sUAS in complex low altitude airspace.
What's sUAS?
sUAS is small unmanned aircraft systems. By the definition that's kind of been proposed within the community and is used within the community, it's any aircraft 55 pounds. So, you know, it's a pretty big range, but most of the traffic that you're going to be assuming and thinking about is, you know, the DJI Phantoms and your drones and whatever other aircraft you see, you know, delivering or going about, zipping about in the airspace, low and with a lot of supervision. So with that in mind, how do we start talking about moving these aircraft into the airspace? So currently, within manned aviation, these are statistics I got from the FAA website, and at any given time, there's roughly 5,000 manned aircraft within the airspace flying. And these aircraft are coordinated by air traffic controllers, largely by voice for the traffic coordination. And most of this traffic coordination is focused around airports. And it's really allowed for the generation of a very safety-conscious airspace. And so that's one of the reasons that it's so infrequent that you hear about crashes and other accidents within manned aviation. And so then if we look at what we're looking at for the unmanned side of things, it's estimated that at least 1.1 million and 110,000, I'm still missing a zero there, commercial sUAS are currently out there in the world and intending to fly at any given point in time. And most of these aircraft don't require runway. They're usually pretty local, and there's currently required to be one person per aircraft, but moving forward to the idea of using these for lots of, you know, survey missions and delivery missions, the one person to one drone ratio isn't going to hold. And so we need a way to automatically incorporate these into the airspace. And so enter the UAS Traffic Management System, or UTM. This is focused predominantly on low altitude airspace below 400 feet. And one of the big components of this is geofencing, which is what my topic is. So within the air traffic, within the airspace, what does this really look like? What you see here in the blue is all of the manned aviation space, which is where most of your commercial jets are the majority of the time until they climb up into just their transient area. Where we're talking about drones flying, focusing mainly is down in this yellow area where we're below the manned aviation and in all of the complexity that is you know, cities and trees and forests and people and everything that you can have in that low area. So we're looking at how do we fly drones safely within that space. So then that brings in, what is geofencing? Geofencing is the idea that we can create a three-dimensional box around a drone and then confine them within that space. So if you're flying in your backyard, you put one up around your property boundaries and you say, okay, as long as my geofence is there, my respects it, I don't have to worry about the neighbor's house or interfering with any other air traffic that's in the area. It also works in reverse. So if you're living next to an airport, there can be a keep out geofence around that prevents you from getting too close to where the manned aviation is. So if we look at, this is a subsection of the area near New York City. If we imagine that this green area is in fact a keep-in geofence, then the idea would be is that you can have traffic going across the river back and forth. As long as it stays within the green area, then it's allowed to be flying there. What you see in the red are examples of keep-out geofences. So I've put those over islands that exist within this river. The idea being that you don't want those aircraft flying over where there's a high population area. And so if you tell your drone that this is where the geofences are, then the idea would be that it can fly anywhere within the green and it'll avoid the red areas. And so you can safely operate within that space. And since these are all based on physical markers that are always there, there's always people on the islands, the river's always there. This is an example of a permanent or a static geofences. If we then imagine that there is a emergency vehicle that needs to cross this area, say it's a helicopter or an emergency flight or a police vehicle that needs to get from one side to the other, it can come in and say, hey, I need this airspace because I need to transit through here quickly. And so in that case, it actually overrides the boundaries that are already there for the period of time that it's going to occupy that airspace. So we call this a durational geofence or a dynamic geofence. And so that actually, now that there's a red boundary there, anybody else that's in that airspace knows to go out into the green areas and stay out of the red while that vehicle's transiting through this airspace. So that's kind of the high level of what geofencing is doing. And so what we're focusing on is both looking at this problem of how to implement these and how to track them from the individual vehicle side and from the system side. To make this the most useful system possible, we're focusing on non-convex. We're not enforcing any convexity requirements, so our geofences can be really any the horizontal boundaries can be any shape we want. And we do want these to be enforced, time-dependent geofences so that you can trust that nobody else is going to violate your geofence and that it's only, geofences only exist as long as they need to exist to kind of keep the airspace less cluttered. The contributions of this work are using polygon set operations within this interface to track the creation of these geofences. We've developed a algorithm and a benchmarking method for detecting whether or not geofence is being violated. And we've defined an algorithm to automatically scale geofences inward and outward to maximize the usable airspace and to be able to provide warning layers, which I'll get into in a bit. And we've also done a lot of the simulation, and we've implemented 3 distinct guidance modes. So that's the response to when a geofence is potentially violated. Again, all of this we'll get into a lot more. The innovations are, in fact, a formal definition of the UAS-centric geofence, which has actually been missing in the community so far. Most of the work that's been done, everybody's coming up with their own locally used definitions. So we've designed one that should be adaptable to any use cases. These are 4-dimensional geofences, and we have a way to store them within a centralized system so that we can track at any given point in time which geofence are and are not active. We have a custom algorithm called triangle weight characterization with adjacency that allows us to quickly, over time, track exactly where we are, which is faster than what the normally used algorithms are. And we have a guidance mode that's been unique to us and actually been picked up throughout the community called local Loiter, which is the idea that when you detect a violation, you don't just stop where you are, you don't fall out of the sky, you actually back off from the geofence before returning control back to the users. So to get into all of this, this is the outline, so that was just the introduction section. I'm gonna go through the geofence system, then how we check for boundary violations, layering of the boundaries, and then a system in conclusion. Most of the time is gonna be spent on the system and the layering of the boundaries, but we'll give a little bit of each of the other sections as well. So to get into the geofence system, we start off with what is our geofence definition. You can see it across the top there, and I'm going to break it down into 3 different sections. The first is how do we define the boundaries of the geofence itself. Our first way to really think about it is it's a list of vertices for our horizontal boundaries, and then we have a flat altitude floor and ceiling. And so with our horizontal boundaries, greater than 3, or greater than or equal to 3, so you have to have at least a triangle, but we don't have an upper bound. And what we assume is that each of these vertices are connected by straight edges and that they're not self-intersecting. So the one here over on the left is acceptable, whereas the one on the right, if that is what you actually want for your geofence, you have to define it as 2 separate geofences because of that self-cross in the center there. So that's our horizontal boundaries, and then if we move on to our vertical boundaries, Like I said, there's a flat floor and ceiling, and this really matches what a lot of the airspace is right now, which is a lot of just altitude layers, when you refer to them as partitions. And so what this really lets us do is, whenever you're just checking that you're within your correct altitude band, you're only doing a greater than or less than check. It's not a complicated process, and it's simple to understand what it looks like within the system. So that's the physical boundaries. So where are these how are these related to the world? And so that's where we have a home position. Our home position is generally going to be latitude, longitude, and altitude with relative to mean sea level. And so that's going to be our local origin that the list of vertices and the altitudes are going to be relative to. Within this, with the examples I'm showing today, it's all going to be just relative to a local coordinate system to avoid the decimal places that inevitably occur when you're dealing with latitude and longitude. So that's just for that. The other interesting part of this is the time component of the home position. So for a static geofence, which is something that's always there, a military base and airport, we have our time component starts at 0 and goes to what is effectively an infinite horizon. From there, that's our static geofence. From there, we have durational geofences, which is the idea that it appears and disappears, but it stays within the same location the entire time. So this would be if you wanted to fly in your backyard, or if you were, say, a realtor and you wanted to do a survey of a house overhead to kind of put that on your website. That's where you would use a durational geofence. The final type is a trajectile geofence, which is shown here in the cyan. Let's move in through there. And so that's really the most commonly referenced usage for drones, which is the delivery model, the A to B model, where you're trying to move through a space. And so within most of what I'm presenting here today, we're going to take that trajectile geofence, and if you wanted to implement that within our system, you're going to break that down into a series of durational geofences. And so we're really just going to focus on static and durational for all of this. But trajectile can also be simplified into looking like a durational geofence if that's more of the mission that you're using this for. Okay. So then the final term is our add IDs function, which is our permissions function. So this is saying who is allowed to access this geofence. So if it's your backyard and you're the only one that wants to fly there, you're saying, okay, only my drones can fly here. But if you're friends with your neighbor and you say, okay, they can fly here too, then you have your drone's ID number and your friend's ID numbers. For more open public spaces, so for maybe your local flying field, maybe you have to be a member before you can fly there. And so you have to get your ID on that list, and then anybody who's a member can fly in that area. Alternatively, it could be like a public park where they just have, okay, no more than 10 drones can fly here. And so then when you request that geofence, you have to check whether the system checks whether or not it's already at capacity. And you potentially have to wait until somebody else lands before you can take off and use that geofence. And so this is really where a lot of the policy that's going to be springing up around these geofences is going to be enacted, which goes into property owners' rights and who can fly where and who has that ability to determine that. And so that's all encompassed within the add IDs function. So that's how we implement it for an individual vehicle. How does it look really from the system side? Again, we're going to stick with the same definition, so it's going to move through it and be useful that way. Our first task is we want to be able to track both the geofence and the vehicles that are occupying those geofences, because it's not just what airspace is used, it's who's using that airspace. And so to do that, we're defining our UTM system with geofences that are sorted temporally and then spatially deconflicted. So I'm going to go through the temporal side, and then I'll go to the spatial side. And so we'll track it that way. So we're going to divide this up into temporal periods, which is just a space of time where all of the geofences are constant. And so there's no change within that space. And we define it as, it's defined based just on a start time and a list of geofences that are active during that time period. We're going to constrain the complexity of it by saying that there's a minimum of 5 minutes per temporal period, which is something that can is going to be useful depending on the airspace, but will likely, urban setting, 5 minutes is a really long time, but in a very rural area where there's not much traffic, 5 minutes is more than enough space. So what does this really look like? When we first turn on the Geofence system, you have a single period and it starts at 0, and there's nothing there. No geofences have been requested yet, it's just an empty period. So then we have a first geofence request, it goes into the system and it says, okay, can I have this airspace? There's nothing else, there's no other geofences active during that time, and so that becomes part of it, and we now have 3 temporal periods. One for before that geofence exists, one for while it exists, and then another for after it exists. And so so a single case, okay, easy enough. Then we get a second request that overlaps but doesn't actually align with any of the same time boundaries. And so when this gets approved, we actually end up with 5 different temporal periods where numbers 2 and 4 are both, there's only a single geofence occupied, so those are the full boundaries that are requested. But the interesting one is down here in P3, which is where the spatial deconflicting is going to come into play. So with those geofences that are now created, who has permissions to fly there and how do we track that? With our permissions constraints, we look at each of them and we create a list of the active or scheduled users for that geofence. And so for our timeline, again, what that really ends up looking like is we have a list for each of the periods with an entry for each of the geofences, and within that is the list of UAS that are active within that period. Okay. So that's how we're tracking who's using them or who's scheduled to use them, and that allows for the monitoring of the airspace itself. So then if we take a step back and look at the spatial side of things, we'll start with the altitude because those are our flat boundaries. So when we have 2 geofences, again, this is the same ones. We have the blue in our, that was requested first, and then the green, which was requested second. And so we have to deconflict green from blue. And so what we really want to do is we want to maximize our usable airspace for green. Blue has priority because it existed first. So what we're going to start by doing is partitioning the green boundary based on, again, similar to the temporal, we're enforcing a resolution. So this is a 5-meter resolution here. So each slice of airspace is at least 5 meters thick. Okay. And so we separate that into 2, we separate the requested geofence into the upper and lower. The lower geofence doesn't actually interact with the blue geofence because it's just different altitudes. And so we then end up deconflicting, we have to horizontally deconflict the upper green geofence from the blue geofence. And then that allows us, we can return both the 2 green boundaries to the user and say, these are your usable airspace during the overlapping time. If we look at a more complicated example with our lovely new cyan, so this is our 3rd requested geofence, and the other 2 have already been approved. So we now have to deconflict the cyan boundary from the existing geofences. And so to start off, we again partition it into our altitude bands. And as you can see, only the 2 right here are the ones that we really need to concern ourselves with for deconflicting from the green areas. And so to start with, we do the horizontal deconflict at each altitude. And then because this is a much wider altitude range, we can actually then recombine these sections where we can reduce it from 5 to just 3 geofences because they have the same horizontal boundaries. And so we can combine them to have these shared altitude. And that way we can reduce the complexity of our system moving forward. Okay, so that's the vertical. So then how do we do that horizontal deconflict? We're going to use polygon set operations. So if we start off with 2 overlapping polygons, where if this was, one's already been requested and the new one and the other one has been approved already. We start off by noticing the existing vertices, and then we introduce additional vertices wherever any of the polygons intersect with each other. From there, we can take those new vertices and actually recombine them depending on what set operation we want to carry out. And so from this, just from those vertices lists and knowing which polygon they originally belong to, we can take the union or the intersect or the difference or the XOR of any arbitrary polygon. And so how we're going to use this within geofencing is for the UTM, which is what I was showing on the previous slides. What we really want to do is if green already existed and we're requesting the blue, we have to horizontally deconflict, we take the difference. And so then only the shaded areas are returned as usable polygons for the user. Is that okay? The upper side, the union, is if you're returned and you have multiple geofences that you have been given permission to use, you would then take the union over those approved geofences so that you have the largest possible contiguous horizontal area to fly within. Okay. So this is how we're manipulating the horizontal boundaries of our geofences within the UTM system. So another example to hopefully solidify this a little bit more, for this one, we're imagining that the ones on the bottom here already exist and are approved within the geofence, within the UTM system. And so then we're requesting this lovely yellow geofence that is intended for, say, a power line inspection. And so we ask for that geofence. And then when that is approved, we get, again, separated out into 5 different temporal periods, where for each period, the geofences are, the yellow geofence is deconflicted from the existing 2 geofences. So what this looks like in 3 dimensions, because we're flying in 3 dimensions here, we get this area where for the first hour of the existence of our survey geofence, it's actually separated out into 2 different disjoint sections, which means you can't actually fly from one to the other with the currently requested geofences. When we get to P4, it's even more broken up, but because the vertical boundaries of the green and the yellow are different, you can actually possibly hop over the green if you change your altitudes there. And then with P5, you finally have access to that center section and can make it across the whole area. So 3-dimensionally, what this looks like is here you can kind of track what's happening. They appear, and then as blue disappears, we then have that space. But at no point in time do we have access to the entirety of our requested area. Over time, we can access all the different components, but we can't actually access them all at the exact same time. And so then what that looks like is if you assume that you have to start from 0 and proceed to 20, maybe you're surveying something over on the side, then you start off there and you have to go slow so you don't hit that blue boundary. So here we go again. Okay, so you're going really slow so you don't hit the blue because you don't have permission to fly there, and so you're waiting. And then as soon as that disappears, you have to make it all the way across for the rest of your time, and so you're racing much faster then, and then hopping up and over that green boundary because it's taking up where you want to be flying, but you have permission to go up and around, and so you do still get the entirety of your area that way. The other way to do this would be if you can start from the other side, then suddenly you can make it across from where the green's going to and survey that area first at your desired altitude, and then just wait for the blue one to disappear to finish the rest of your survey. And so this is the simple 1 vehicle case. Especially if you start adding more vehicles and more varied flight plans, there are infinite number of ways that you can cover this same area. But this is the simple idea of how they interact and how it is going to impact the flight plan of the people that are actually trying to use this airspace. So that's our high-level introduction to what is the geofence, what is our formal definition of it, and how are we tracking them compared to each other. So the rest of this, the next couple sections are going to be focusing on a single geofence at a time so that we can really get into the nitty-gritty of how does it work for the vehicles that are running this system. So to do that, we start off with our boundary check algorithms. This is how do we determine whether or not we're respecting our geofence boundaries. So we start off again with our geofence definition and a single keep-in geofence, where again, we can just check the vertical boundaries with simple inequality. This is actually just an application of the point and polygon problem, if you're familiar with that from computer vision or graphics or computational geometry. And so the most commonly used method is ray casting, and the one that we're proposing as an alternative is triangle weight characterization with adjacency. And I'm going to kind of fly through this section, but if you want more information, it's in papers. So triangle weight characterization, what we do, we start off with our funky polygon, and we divide it up into triangles. And then from there, once you have triangles, you can, because it is a convex hull in 2 dimensions with 3 inequalities, you can determine whether or not you're occupying any of the triangles. And then with that simple check of whether or not you're in a single triangle, what we actually want to do is then create a graph. Because we're a vehicle moving through space and we are not teleporting, we know at any given time we're probably pretty close to where we were previously. And so as we proceed and fly through here, we're assuming we're always within the same triangle, or we're then doing a breadth first search of the adjacent triangles, where adjacency is defined as a shared edge. And so as we continue to walk through, it's fine, but then suddenly if we violate our boundaries, we have to suddenly check all of the triangles for containment before we know that we're actually outside. And so to remedy this, we actually add a bounding box around it, which is just a simple rectangle that we again divide into triangles, and then we actually add that into our adjacency graph. And so now we know that even when we're outside the geofence, we're still somewhere within that graph. And if we make it beyond that bounding box, things have gone very wrong already, but the bounding box can be, again, checked with just a simple series of inequalities, and so it's a very quick procedure there. And the number of triangles here is still just scaling linearly with the number of edges, and so our runtime is still very contained, which is what we're looking for here, because ideally this is running on board at the same or a very similar pace to what your autopilot's running at. And so that is where this is letting us really go, and it lets us be a lot faster. We have a lot of really cool results plots within the papers that have been published on this. And what this really lets us say is that once those triangles have been generated, our average expected runtime is much faster than what the other methods that are usually used for this within geofencing are. So that's how we're checking our boundaries and how we can how we know where we are within respect to our geofences. So from there, there's the question of, okay, now that we know whether or not we're inside or outside, how do we prevent that violation? Because again, leaving the geofence is actually really what we don't want, because once you're outside the geofence, you might be actually in somebody else's. And so that's not really a good thing to let us do. So what we want to do is we want to be able to say to stop or turn back prior to violating that geofence. To do that, we're creating these scaled boundaries, these extra layers of the geofence, so that we know to stop or override the nominal guidance before that violation actually occurs. And so for both a keep-in and a keep-out geofence, we're generating 2 additional boundaries, where the one closest to the original one in blue here is our override boundary. So if you get to that point, the geofence system is actually just going to take control and pull you back to where you're supposed to be, so that you're not, to really prevent that violation of the original black boundaries here. The green boundaries are the warning layer, which lets you tell either the autopilot or if there's a human operator attached to it that, hey, something's gone wrong, you're very close to violating your geofence, correct something, or I'm going to correct it as soon as we get to that override boundary. So how do we generate these, and how do we know how far to put these boundaries out? So to do that, we're using buffer distances. The simple idea is that you would want all of your boundaries to be at least a set distance away, because whatever the known turn back or the stopping distance is. So you want a uniform boundary all the way around, which here we're using as delta U for a uniform boundary. This is a keep out geofence, and I'm kind of visualizing that distance as the radius of the circles that you see at each of the corners. So then that's uniform, but that's really constricting if you have a strong directional component, which is why we have our directional buffer distance here. And what that really lets us do is it lets us take into account things like known sensor drift or wind, which is what's shown here. And what that ends up looking like is just a shifting of a second circle of the same radius, but you shift it by the distance that your directional buffer needs it to be. And so here we've got an easterly wind, and that is so if this is a keep out geofence and you're flying towards it, because you're with the wind, you need more space to stop, right, or to turn back. And so that's why it's a larger distance here than it is over here. And so for this, we have the same uniform distance all the way around with that additional padding on this side to account for that wind and that directional component. So how do we calculate this? For hover-capable vehicles, which is your quadrotors, your octocopters, whatever your custom build is that can just sit up on its tail, for the uniform, we're just using a simple distance with assumed constant acceleration calculation, which pretty straightforward, probably recognize this from like high school physics. It's just our airspeed squared over twice the acceleration that we're going to be commanding. Then for our directional component, we're using the same equation, just with the addition of wind, and then we subtract off our uniform buffer so that it's only in the direction. We only apply this on the side of the geofence that we want it to be on. Where this gets interesting is with a fixed wing aircraft or something where you have a minimum forward speed at all times. And so what you see on the bottom is just a uniform buffer all the way around with a nice little turn angle. And so what this is it's just the airspeed divided by our turn rate that we're going to be commanding in that turn back. And so it keeps flying straight until it hits that blue boundary, at which point the geofence activates and commands a maximum turn, and then it releases it back to the nominal controller as soon as it's perpendicular to that edge. So that's what that one's doing. And nice, easy equation there as well. Where it gets interesting is when we look at the directional side. And so to do this, we're looking at the at aircraft equations for doing the turn within wind, which is what you see up there. And then if we look at the velocity component of that, we can solve it for t, and that actually gives us the additional time required where if you're flying with the wind, so moving faster than what your airspeed's reading, you're suddenly, this is the time that it takes for you to make that first turn and to stop your forward progress in the wind. Okay, and so what that ends up looking like is we take that time and we solve it for our maximum, we solve it for the distance traveled with the wind. And so what that lets us do is we can put those equations together and get that video that's there on the bottom. So again, we've got an easterly wind coming in. And so what you're going to see here is it's not going to activate until it hits the blue, but it's going to be nowhere near the black. But yeah, so for fixed wing, this is how we would be determining our uniform buffer and our directional buffer. And so because we have these equations for both vehicles that are capable of stopping and coming to a hover and those requiring a minimum turn radius, we can then use these buffer distances moving forward in our calculations. And so how do we generate these geofence boundary layers? So we start off by smoothing the boundaries. And by that I mean these are randomly generated geofences that I'm using, but what you really want to do is to simplify the rest of the math, is remove any components that are too small to be seen, too small to be used in the scaled version. And so here within this picture, the blue lines are the changes that will be made to the boundaries once, if you're moving inward, and the green ones are if you're moving outward. And so we're actually we're modifying those boundaries to make them simpler and to really preserve the shape without while doing minimal changes to what it actually is input as. And so what this lets us do is that with each of these, we have two different smoothing algorithms that we're showing in blue and green. And so over here, what you can see is that the red boundary is clearly doing something weird where it's not a valid boundary anymore, whereas both our blue and our green boundaries for inward are still valid. And what you would expect really for that shape if you were trying to scale it inward in a simplified manner. Same over here, we see that it's actually just taking off this little corner, but still, again, the majority of the shape is preserved while reducing the number of vertices here. And so what we've seen is that this actually really increases the success of our scaling algorithms moving forward. So to actually scale the boundaries, we can't just take the vertices and multiply them by our delta, by our desired scaling factor, because for non-symmetric boundaries it doesn't work, and especially once you get into our concave messes of geofences, it doesn't work at all. And so what we actually do is we go edge by edge and scale them inward by our distance. So it's consistent through each of the vertices as much as possible. And so to do that, we start off by just analyzing the existing polygon and noting the equations of that shape of each of the edges. And then from there, we take each of those edges and we project them either inward or outward, depending on which direction you want to be going. And what we really focus on preserving is that the slope of each of the edges is preserved as we move inward. And so by keeping that same slope, we just we define the new vertices as where the new intersection points are between each of those edges. And this is really where the smoothing helps, is because once you're projecting inward, if there's edges that are too short, that the projection inward kind of closes them in on themselves, that smoothing gets rid of it, so then we do have this nice, simple inward movement. So once we have this scaled geofence, which for the simple cases looks like, okay, we're done here. But actually, especially as you get into weirder things, there's two more functions that we really want to execute before we move on. The first is flatten vertices, and the idea here is that sharp vertices end up using up a lot more airspace than they need to. And so if we scale these inward and outward, we're actually looking at any of the angles that are greater than 180 degrees in the direction that we're scaling. And so here they're circled in red. And what we're going to do is we're just going to replace each of those vertices with another. We're going to add an additional vertex at each of those points, so that we actually end up with a flattened edge across each of the vertices that's perpendicular to the angular bisector of the original angle. And so what that actually lets us do is we regain a lot of usable airspace. The ideal or the optimal implementation would be to use arc, but because one of our design parameters is that we're only using straight edges, this is our solution. And if we look at the comparison of the area that we regain functionality with, the dotted lines is how much area we would regain using an arc, whereas the solid lines are how much we get back using only the flat edge. And so what this shows us is that we're still getting the vast majority of the usable airspace by using our method and keeping it only with straight edges instead of starting to incorporate arcs. So that's where that's going. So then the final step is our cross-check, and our checking for correctness within our scaled polygon. So here again, if we start with our black boundary and we scale that inwards, we've got this lovely narrow passageway that closes in on itself. And so obviously this is invalid, but we can see that both of these end triangles are still useful. And so we want to be able to salvage that. And that's what cross-check is doing, is we start off and we look at, okay, where does our scaled boundary intersect with itself? We divide those into their own little subsections, which we then recombine to create the polygons that make up our scaled version. And so from there, once we know that, we can actually check to make sure that the vertices and edges that define those polygons respect our desired buffer distances, and then eliminate any of the ones that don't comply. And so with the addition of this final step, we can actually retain the two sides without having to redefine the original geofence to eliminate the narrow passage between them. And so this is all, great and big pie in the sky, but what does this actually look like? And so to test it, we did a Monte Carlo style simulation. We've generated a lot, 3 million different unique geofences from 3 to 27 vertices. And for each of those, they're confined to be between 100 width and 100 by 100 in the horizontal plane. And so from there, we actually test them for the uniform and directional boundaries, each combination, and they're tested for both inward and outward scaling. and each of those scalings is done using the 5 different of our smoothing setups. So what does that actually end up looking like? If we define success as where there is at least one section of the geofence that returned as a valid flight area, we can actually see that we're very close to, or definitely above 90% for all of our inward cases, except for the very small number of vertices. And where the majority of the, when we're having 3, 4, and 5 vertices in our geofences, that's just because we don't have a minimum size constraint. And so that's mostly geofences that are just too small that when we try to scale them, there's nothing left. They already closed in on themselves. And so they're, if we had a minimum area constraint, those high failure numbers on the far side there would likely disappear. For our, if you then look at the right sides of the plots where we're in the very high numbers of vertices, where this starts falling apart is in that complexity. Because again, we're scaling by the same amounts, but we're adding more and more vertices, which means we're more and more likely to get some of those closed-in regions on themselves. And so what's that actually look like? This case technically failed both inward and outward scaling. So our green boundary here is our outward scaling, and the blue boundary is inward. And so we're going to zoom in on this little section here. And so what we're looking at is, let's look at the green first. So green is our outward scaling, and the red solid line and that dotted line are connecting the boundary, the vertices from before and after they were scaled. And what you're seeing is that little cross up there tells you that you've actually caused a switching in the order of vertices that's led to this little bitty nub being too close to its to the original boundary. So that's why that is a failure case. We see the same thing over here with blue, where the red lines cross, and it's what most of our failures look like for this data set. And what this is really telling us is that our smoothing algorithms can be improved, because if this was properly smoothed, then this edge for our inward scaling would have been removed, and this would have just been a single vertex instead of the 2 we're seeing here. And for the outward case, it would have removed this upper black one that I can't quite reach. But that would have, again, reduced this section down into just one vertex, so there would be no edge to cross itself there. And so that does suggest that there's additional work that can be done in the smoothing to further improve these results numbers, particularly on the far side of these graphs. But that is those are the failure cases that we're seeing. Okay, so that's big picture. What's the percentage that we're successful with? What's failing? But I said we are using 5 different setups. And so here the black is just our results when there's no smoothing at all. And this is for when we're just using a buffer size of 1, a uniform buffer size of 1. And so there's a clear distinction between what the smooth ones and the non-smoothing cases, but you can't really see the distinction between each of the smoothing algorithms that we're using here, because they're largely, if one succeeds, most of the other ones succeed as well. And so they're very consistent as far as the definition of success here of at least one valid polygon. But they're not the same, and so we wanted to see how do they compare to each other. And to do this, we introduced an area difference metric, where you take the non-overlapping area and divide it by the total area of the single polygon. And so for this, if we are considering how much space, the area difference between the blue and the green, where blue is our main solution, we're subtracting off the area that's also contained by the green. So then it's the shaded area divided by all of the area contained within the original blue boundaries. So this is our area difference metric, which if we look at the angular smoothing and our edge smoothing, which are our 2 main options here, you can see that for the solid, the solid line is saying, okay, for the cases that there's no smoothing at all, what area do they contain that the smooth cases do not? And so that's a pretty constant percentage of the area. Whereas if you look at the ones if you look at it from the other direction, where what does the smoothing case incorporate that the original case doesn't, we see a huge increase in, we see a consistent increase in the area difference as the number of vertices increase, which is expected because you're removing those areas that are closing in on themselves, and that gives you, by approximating that, you actually get that added area back. And so this still isn't really showing what the difference between the different smoothing algorithms is. And so to do that, we're comparing, this is angular versus edge smoothing. And what you can see is they're still very close, but there are definitely cases where one is a little bit better than the other. And for this, for the results we got, edge smoothing has slightly more usable area most of the time, but they're very closely knit. And so really what we want to be doing is run multiple smoothing methods over each geofence and then just selecting the result with the most area, so that you then have, because again, from the user side, you just want to maximize the area that you can use for your flights. So that's layered boundaries. We have an early version of this work that was published last year in a conference, and a journal paper that's hopefully coming soon. It's been submitted, so it's in the process. And then the final really interesting section here is how do we combine all of this back together? So I've shown you a bunch of individual components, but what does that actually, it's pretty disjoint at the moment. So we're gonna go back to our lovely blue and green geofences which are slightly offset. And we're gonna say, okay, we're interested in our green geofences as it's been deconflicted. And so we pull it out and we look at each of the two sides where this, our lovely rectangle is the lower portion that didn't have any conflicts, and this one is our upper portion. And so we take those and we generate the layers for them. And as you can see, we have some of the edge flattening going on here, which is why these are much nicer boundaries, or they're not a sharp spar. There's a lot more usable area. So then from there, we divide not just the original geofence and the bounding box, but each of the layers as well into triangles. So we're tracking where, whether we're within our desired flight area inside the green, or if we're in our warning area, or are we in our override area, or has something gone horribly wrong and we need to do something else. So if we then consider we have a couple little quadrotors flying through our area, and then as soon as they violate, if for some reason they manage to get a waypoint that's outside of the area, outside of their original geofence boundary, as soon as they start crossing the blue, we bring them back and down to the green. This is our local loiter guidance mode, which is really, as soon as we hit the blue, we begin decelerating the vehicles, and then we bring them back into the warning area. So the idea here being that you want to bring them back where there's far enough from the boundary that they're not going to just immediately violate the boundary again. And so this is our favorite of the guidance modes. The kind of default, familiar to everybody idea is the return to launch. And this is the idea that we're going to make a beeline straight for our home position, which is okay, but not great. Because actually, if you watch the one on the left, we're getting a full geofence violation there because of this guidance mode, which is the exact opposite of what we want to be happening, because our override boundary is stopping us from actually from violating it on the top, but then we're then actually causing a full geofence violation in our response. And so to adjust for that, we introduce a simple additional path planning step to it, which is that once you're within the green, you either if you can't make it straight to your home position, you employ a simple guidance mode such as wall following or tangent bug is written here, where you then stay within that green boundary and you just follow it until you can get your clear line to the home position. And so these are some of our proposed guidance methods that are, again, pretty consistent with what's being used out there and what we've put out there as we're moving forward. So that's kind of our that's what the system looks like when you're using it as a full system. And so, again, some of this work has been presented already at conferences, but we're in the process of wrapping that up into a journal paper at the moment. So then, I guess the final part is just the conclusion of all of this. And so what this thesis has really been about is that as far as I know this is the first Geofence system thesis where we're really looking at it not just from the UAS side or the system side, but combining everything into a consistent system that's using the same rules for each of the components. And to do that, we've defined that system as a temporal and spatially separated whole group. We've created an algorithm that lets us quickly determine, using prior knowledge, whether or not we're violating our geofence and where we are located within our response requirements. And we've developed the boundary scaling and the guidance methods. And so all of that comes together to what lets us have a system, at least in simulation, that really does well for both the UAS side and the system side of managing these geofences and allowing their creation and propagation. And so looking forward to what else there is to be done, it's huge. I've written out a few of our possibilities here. I do really think one of the next things is the trajectile geofences and making sure that those are something that's usable, especially when you're looking at moving over a great distance where there's a lot of other geofences already in the area, because you do need to make sure that you can get all the way from A to B. It doesn't work if there's a block in the center that you just can't cross, right? You need to be able to plan around that and to know that. And so getting that implemented either as a series of durational geofences or as its own, or as a larger full path understanding is something that really is next on the docket to be done. Like I pointed out in the layering section, there is a lot of work that can still be done with finding new smoothing methods and ways to kind of streamline and improve those methodologies that I'm using currently. And I mentioned wind a lot, but really the directional and the uniform buffers can be used for things like sensor noise and other known disturbances, and to really making that a more robust mathematical representation of what the vehicle is doing and what you can expect from it is really what we want to be doing. And all of the geofences I showed here were either manually plotted out by me or randomly generated by MATLAB. And so I think one of the really cool things moving forward is going to be combining the random and the manually defined with existing maps like property maps and GIS databases, and incorporating all of that information to really show to give an even more accurate representation of what the airspace might be looking like, instead of now that the base work has been done to say this is how it all works together. And then looking even farther into the future, this was all assuming that your geofences working in your vehicle are working properly, and so there does need to be some fusion with other emergency systems for when things are really going wrong. So planning your path to a good landing site, depending on how much control you have over that, and really just the handoffs between the nominal guidance and the geofence guidance and the emergency system can all be synced up to again make this a much more deployable system. Also, like I was saying, with the additional maps, there's a lot of interesting work that can be looked into, where that considers, is it reasonable to say 5 minutes at a time is a solid chunk of geofences? What kind of communications are we assuming? How often are we updating from the cloud? How quickly is that airspace changing, and what does that mean for what our vehicles need to understand about the airspace and our communication requirements? And with all of that, there needs to be a lot of flight testing. Most of this has been done in simulation. Some of the guidance stuff has been developed in flight testing, but the vast majority of it is simulation-based, and I think there's a lot to be learned, especially with the buffer distances and our guidance modes, through the flight testing, not just with hover vehicles, but with fixed wings as well, because while you can anticipate a lot through simulation, there's a lot that the real world's just going to make very clear very quickly. And so I think flight tests moving forward are really should be a big component of the future geofencing work. And with that, I'd like to open the floor to questions.